Well, let's look at some example problems of applying uh, Faraday's law, which we got some numbers involved anyway. So the first one is the following problem. We've got a planar circular coil that has a radius 10 centimeters and it has 15 turns or wraps in it. And it's placed in a magnetic field that's uniform. But it makes an angle of 30 degrees to the normal of the area enclosed by the circular coil. The magnetic field strength, though, the magnetic field is always pointing in the same direction, its magnitude changes with time. So this is a case where we change the flux by changing the magnetic field as it changes with time. And in this case, it goes from B1, which is 1 Tesla, to B2, which is 5 Tesla, in a time interval of 10 seconds. And then what's wanted is what's the EMF generated in the coil, and if the total resistance of all the wire that makes up that coil is 15 ohms, what's the current that flows in the coil as that magnetic field is increasing at a constant rate from 1 to 5 Tesla. So I drew a crude picture of it. We've got a circular coil, 15 turns, radius 10 centimeters, and then the magnetic field direction, it's always pointing in the same direction, but it's getting stronger. But the angle that it makes is this 30 degrees. So I first calculated preliminarily the area enclosed. So it's circular, and so I know the area of a circle of radius 0.1 meters. It's given in centimeters, but be sure to convert everything to MKS units. So don't use 10 here because that'll get you off by a factor of 100 as it turns out. But instead convert it to meters, 0.1 meters, square it up, and you find that the area that's enclosed by one of these loops is 0.0314 square meters. Now we're ready to do magnetic flux. The magnetic field is not constant, but it's constant in direction, and it's uniform. So the area is fixed. It's constant. It's always in the same direction, and it encloses the same area, so the area vector is the same. And so the flux through one loop is just B dot A, and that's the magnitude of B, the magnitude of A times the cosine of theta, the angle between the two. This B here is changing, so the magnitude changes, it actually increases. So there's where the time dependence is. Everything else is fixed. So this is a case where the field strength is changing. We can plug in the relevant numbers, the area we just calculated. The angle between the normal and the magnetic field is 30 degrees. And when I plug those numbers in here, I got that the magnetic flux for any B strength, magnetic field strength, was this value here, 0.272 square meters. And now I'm ready to use Faraday's law. Faraday's law is really this, but when the flux is changing uniformly, that's the same as, and again, I'm not worried about the direction of it. Here in this case, I only want to get the magnitude of the EMF that is generated, induced in it, is N. And for uniformly increasing fields, uniformly increasing fluxes with time, that just is the same thing as delta phi over delta t. And I can get those. Phi b at the later time is just B2. And at the earlier time, it's that same factor times B1. Or if you like, you can factor out the 0.0272, which I did here, delta B over delta T. That's the change in magnetic field with time. That explicitly displays it. In our case, N is 15. The area was this. And delta B, the final was 5 Tesla. The beginning was 1 Tesla, and it did that in 10 seconds. So the time interval delta t was 10 seconds. If I carry through the units and work through this, do all the arithmetic, I get that the EMF is 0.163. But the units are what? Well, Tesla meters squared per second. And so there you have it. The EMF was 0.163 Tesla meters squared per second. And if you took that to your boss, even the NBA knows that voltages should be given in volts, right? So he says, go back and, I don't know what the heck a Tesla meter squared per second is. You say, well, a Tesla meter squared, that's just a Weber, so I could also call this a Weber, or a Weber per second. But what is that? So how do we relate these two? Let's look at what is a Tesla meter squared per second. Well, first I need to remember what a Tesla is, and I never remember what a Tesla is in terms of more fundamental things that I do remember. But I do know that, like for a straight wire, one has a force is equal to I L vector cross B, and I could have chosen some other expressions here, but this is one that's just quick and easy to do. And so if I look just at the units of this, I get the units of force is the units of current, units of length, of the wire, units of magnetic field. And I know magnetic field in SI units is Teslas. A length is in meters, current is in amperes, and force is in newtons. And if I solve that for the Tesla, I see that it's a Newton per amp meter. So I can take that and put it up here for this EMF term. So a Tesla meter squared per second, the Tesla we just found was a Newton per amp meter. I get one cancellation of meters here. On top I'll get a Newton meter. And on bottom, an ampere times a second. But now I remember an ampere, well, that's just a coulomb per second. So the seconds go out. And a Newton meter, I remember, is a joule. So I get a joule per coulomb. But remember, a joule per coulomb is what we call the volt. So I could replace these with volts. So 1 volt is a Tesla meter squared per second, or 1 volt is a Weber per second. Either one. In any event, that turns into 0.163 volts. If I now want to know what the current is, what's the magnitude of the current, I know the voltage, 0.163 volts from part A, and the resistor was 15 ohms, and so I can divide that out to get 0.011 amps or 11 milliamperes.